could not be covered, then I will find another time, maybe in the National Week. In that week, I will find another time to cover up the material not covered. Okay, so first I will have our TA, Jiafu, give an online course guideline. So that this course, online course can be run more efficient. And then I will go through the course plan. Then the Jiafu will come back again to talk about the lab logistics. Starting this week, we have 2 labs, okay? And so Jiafu will talk about how to access those FPGA boards. And next, I will give a very general, broad overview on the application acceleration in the market and the industry trends. Yeah. And then followed by the lab 2, I will introduce the PINK. Okay, PINK is a framework. So I will explain more details about the hardware and software, how they co-work together. Yeah. So that for doing the lab, you are not just following the instructions. You will know the inside hardware software co-working mechanisms. And at the last, I'm afraid today I may not be able to cover the last items. We may run out of time. This is a general overview from gate to HLS. That means from logic gate and to Verilog to high-level sensors. Give you a feeling that how high-level sensors can benefit from the traditional design process. So basically, I lump a year of logic design, the Verilog in one lecture. Yeah, just to give you, if you forget how to do the logic design or how to write Verilog code, it's a quick overview. Okay, so so I have Jeff talk about this course the guideline.
Okay, I'll share my screen.
Yes.
Can you see the slides?
Yes.
Okay. Okay. Hi everyone. I'm the TA of this course, Liu Jiafu. Before we start the class, here are some rules for you. You have to follow the rules. First of all, you have to use your real name to attend the course from next week. You can change your username in Google account settings. And next, please turn on the video and turn off your microphone. And you can change your background for your privacy. It's okay. And this course, Teacher Jing will give you some questions at the end of each section. You have to answer these questions in chat. You can click this button to open the chat view. And if you have any questions during the lecture, please click the raise hand button to ask questions. And about how to change your background, you can change it anytime in the meeting room. And before you join the meet, and you can click the change background button here. So you can change the background and any picture you like below. And after you join the meet, and you can still change the background by first clicking more options here, and then change background. Okay. So again, I'll say the rules again. first you have to use your real name from next week, and second, you have to turn on your video and turn off your microphone, and you have to answer the questions in chat view. And if you have any questions, please click the raise hand button to ask questions. I'll unmute your microphone and you can say something, and you can ask your questions online. Okay. Okay, that's it for the online guideline. And any questions?
Okay, yeah. So let me take over and share my screen.
Okay.
Okay, yeah. So let's go over this course plan. Yeah. Let me first introduce myself briefly. I graduated from NTU in 1983, so you may know my age now. And then after serve 2 years military.
Sorry, sorry, Teacher Jin, your slides doesn't change the page.
It's nice. Oh, okay. Oh, I need to.
Maybe you need to write something to change pages.
Oh, but I need to touch, right?
Yeah.
Great. That's very well. So I need to. Oh, okay. Okay, and then I went to UT Austin for my master's degrees, and right after I graduated, then I came to Silicon Valley, joining EDA company, LSI Logic. That's actually a SC foundry company. At that time I was developing the EDA tool, especially the placement route system. And after that, I joined a chipset company, Symphony Lab, which is a predecessor of VIA technology. So in 1992, I helped founded VIA technology and moved the company back to Taiwan. So VIA was established in 1992, and since then, VIA is a chipset design company and designed the chipset for Intel and AMD chipsets. And after that, I developed the VIA acquired the x86 processors. So I transferred the x86 processor from Austin to China and start developing the x86 processors. And after that, I designed the SSD controller and then switched to storage system. The storage system we developed is computational storage. In that project, we start adopting the high-level synthesis because I observed the process to design this application-specific hardware in the traditional IC design process. It takes too much time, especially for the hardware, which is mainly application-specific. That means the whole architecture is defined by software. And as a hardware designer, we simply take some of the application code, translate into the hardware. And the co-working between software engineer and hardware engineer is very long and error prone. And let me tell you a simple the scenario of the co-working. First, the software engineer design the algorithms and write the pseudocode. Write the code actually, similar everything is works. And then he identify area that should be accelerated. He write the document and hand over to the hardware engineer. And how there is no way to have a the spec written in such detail that people could understand clearly. So there is always a misunderstanding. So it takes months, maybe 2-3 months, for the hardware engineer finish the hardware coding. At that time, the hardware engineer is very difficult to simulate their hardware because that's a whole system issue, not just a single hardware module. So their function could not be fully verified until put into the FPGA and run into the system. So who is doing the hardware debugging? It is software engineer. Software engineer debug a black box designed by the hardware engineer. So it takes a very long time to communicate. Yeah. So at that time, I find out high-level synthesis is a very good design methodology. So I instructed the software engineer, why not you design the hardware by yourself? Okay. So the first initial implementation, the performance area is way below than the hardware designer did. So after 3 months, they can deliver, the software engineer can deliver hardware, the performance comparable, both performance and area comparable with a 10 years design engineer. Okay. So at that time, I think this design methodology is very promising. So I think Taiwan school or students should learn this design methodology. Yeah. At that time, I also observed since the high-level synthesis was introduced from United States, and then China has a very aggressive. They many school and they have a competition in China. So China has involved in high-level synthesis long before Taiwan. Yeah. So that's the background why I like to come to school to teach high-level synthesis. Okay, so let me state the course objectives. Okay, so the whole course design around these objectives. I hope at the end of this course, we can achieve these objectives. Yeah, that's my exam. So I hope I can get a higher score in this area. Okay, and the score is determined by you, students. First, the basic one is using the high-level synthesis tool to design complex digital circuits. So we are not talking about a simple laboratory and follow the instruction and then do that. Okay, it has to be complicated, the design. And actually, high-level synthesis is not just the design concept. A lot of time you have to use the high-level synthesis tools. So every student has to be very familiar with the capability of those tools. Yeah, they can give you great help. And then everyone should be able to analyze and optimize the design. So there are a methodology how to analyze the design and how to optimize. That's the course will be teaching that. Another area is the independent research on specific application area. Okay, and then we can evaluate, develop end-to-end application acceleration. That's a key point. It's here. It's an end-to-end. So that means you are not just designing a kernel to accelerate a particular function. You want to design the whole system from the application end to the hardware end. That's why I mean end-to-end. So keep in mind, okay, what I want to teach you is not just kernel design. You need to be able to take an application program and then do the profiling and find out the performance area and then move that part to the hardware acceleration. Okay, and when you put everything together, the first time, definitely performance is lower than pure software running in processor. You would then continue to improve, optimize. Yeah. And at last is promote engineering soft skill. Okay. Since people spend time in this class, so I think there are certain skill may be more important than the technical for your future engineering career. So after 30 years of engineering careers, so I see many engineers. Some may not have a very high degree or go to good schools, but they have a much promising engineering career. So I like to let you know what makes them outstanding and special, and I hope you can exercise those characteristics in this class. That's the course material we'll be using in this class. So the main material will be this one. That's the AAHLS textbook. AAHLS is, you know, everything if it's in textbook, that means the technology is mature. Okay, and AAHLS, there is no industry textbooks for that. Simply because this is technology still evolving and it's still changing. Okay, for example, like the Xilinx VTIS2 you will be using in this class, the revision twice every year. So for each revision, they add more feature and make the compiler more powerful. Okay, so it's a moving technology. So put into the textbook. So that's why you could not find the textbook in the industry. You see a lot of technical paper. Yeah. So I try to put into a textbook form, step by step, so that you can learn the technology in a more systematic way. So that's and this textbook I spent next 2-3 months working on that. And yesterday I put that online. So I'm trying out the website. You got to read the textbook from the website, and I'm still testing it. I hope next week you will be able to access. And there are other reference manuals. This one is very popular. Yeah, it talks about the some of the hardware design issues using the high-level synthesis. Mental has a HLS Blue Book. Yeah, that's of course it's a target to the mental catapult tools. And we will use most of Xilinx application node, UG 902. That's the basic one, and then UG 1399 is a high-level synthesis user guide, and 1393 that's a software platform documentation. Those are document maybe 500, 600 pages. Yeah, so but it's very easy to read. I actually capture most of the content in the textbook, but for the detail you can always come back to the original document. Yeah. And there are a lot of supplementary materials will be in the lecture note. So if you want to find out more details, you can reference those papers. Okay, so this course is an 18 weeks course. Okay, and I divide 3 parts. Okay, the first part ends in midterm. Okay, so in the first part, you will finish all the AAHLS studies. Okay, I put all the most important materials and teaching before the midterm. So in the midterm, I will test all the AAHLS knowledge. Okay, and there are labs. Okay, I will introduce the lab in more detail later. Okay, so each lab has, for example, in this first week, we will be doing 2 labs. Okay, those 3 labs basically give you the platform, let you to familiar with the device. We are dealing with 2 devices. One is the MPSoC, which is embedded FPGA, mostly used on the edge end. Okay, this is the pink. Okay, so that's the device you will be using in this week. Okay, you're gonna to set up the tool and run a very simple example to test out how to access this device. And next week, you will be doing another lab. That's for cloud application. In the cloud, people use the PCIe FPGA, like in Amazon. They install this FPGA in Amazon. Okay, so people can write application acceleration running in the cloud environment. Okay, so then this is the second lab. Okay, and each lab for detail, you can look at this slide. The basic idea about the schedule is for each lab starts, it takes 2 weeks to turn in the lab result. Okay. And some of the lab take a longer time. Okay, most of the lab take 1 week. And lab B is more difficult, so it takes 2 weeks. And lab C is very complicated and very comprehensive, so it takes 3 weeks. Okay. Okay, so that's the lecture content. In here, this content is more than 3 hours can cover. Especially, I don't want to speak too fast and cram too much material in the course. So I try to break the material, the presentation into a 20 or 30 minutes session. At the end of each session, I will have certain questions, so that led you to absorb the materials. So it won't run fast. However, it's not enough time to cover all the materials. In that case, I will find another time to supplement the teaching. Yeah. So most likely, I discussed with Jiafu, we will have used Wednesday night. Wednesday night for those material could not be covered in the class. Okay. The first maybe since this national holiday, Monday we don't have a class. Then I may have find Wednesday in this week to cover material left. Okay. So in this course, let me probably quickly go through here. And so today I will introduce the lab. I hope today I can introduce the lab, and then from logic gate to HLS. Okay. And next week we were talking about the second lab, which is lab 3, the XRT, and talk about the VT's development flow. Okay. For this, I mainly emphasize what features in the tool you should leverage to study, and the content of those analysis tools will be supporting your presentation. You should refer a lot of information from the analysis report of the tools. Yeah, so I will tell you the area that you should be particular pay attention to. And then introduction to HLS. So the actual HLS starts from here. Okay, well, I will just give a quick overview. And then next week, then I will introduce basic FPGA. FPGA architecture is very important, especially you need to know the components in the FPGA, so that you can better use the resource. And then we're talking about kernel I/O, and then we come to the very important optimization, pipeline, data flow, and data type. Okay, yeah. So in the whole kernel optimization, there are three optimization architecture, three important architecture in our optimization process. One is you want to leverage pipeline, okay, and you want to use the data flow. Another is SIMD. Yeah. So I will cover this, and the SIMD is in the data type. So in this session, many talk about how to optimize your kernel. Yeah. And the last, before the midterm, the last material to cover is the structural design and hierarchical design. So that means you want to design a whole system, not just a single module. So how do you put module into a system? This methodology will be introduced in this class. Okay, the second part of this course is the application example. Up to that point, you all know the AAHLS basic skills. So let's look at the real applications. That's a much more complicated examples. First, from AI to gate, we will be using an open source platform called Fin. Okay, the Fin I will introduce later in greater detail. And in the second part of the course, I also introduce the RISC-V and SQA. SQA is a simulated quantum linear, and quantum computing is very promising. And in Taiwan or in Japan, the simulated quantum computing basically introduced by Japan because their real quantum computer is behind. So they use the simulated quantum to solve a lot of combinatorial problem. And so we have a student study that. So for the second part, those material we have been working in the past 3 to 3 months. The RISC-V and SQA is from the last course that I taught in the computer science department, the final project. And then I work with the students to turn their final project into a teaching material. Yeah. So those material is not available outside. Okay, that's a purely home developed, and I think it's very important. So I choose these topics and put into the teaching material. And for Fin, it's a very good material. So for later I will introduce the Fin. Yeah, and the last part, the third part of the course will be the final project. Okay, so in the last part, you have a 1 to 1.5 months to work on the final project, and the final project will be a guided process. That means for each team, you have to decide the final project earlier, so that I can have a one-on-one meeting with each team to decide the scope of the final project and how to address the issue and what approach to for the final project. Okay. So for the textbook, it's pretty much in line with the course outline. Okay, we have 12 chapters in the textbook. Talking about the basic concept of AAHLS and the FPGA architecture, and from gate to high-level sensor overview. And this is the application solution development, basically talking about the tools. The I/O interface, pipeline, data flow, data type, and talking about memory architecture is important because a lot of time the performance is limited by the memory bandwidth. Okay, so you will see a lot of time the speed up is because you have a intelligent or smart how you handle the memory interface. For example, for doing the video or image processing, people use a line buffer. Okay, the line buffer is an example. What I mean the memory architecture. So you use a small piece of memory to greatly eliminate the memory bottleneck. Yeah. So in here, I will introduce a few memory caching, those memory techniques, and the structural and hierarchical design. And the last part is the whole system optimization issue. Okay, so for the theme, this lecture, and actually, they are also joining this course. Yeah, Hua Yang and the Ke Han. Yeah. So in the past 2-3 months, they have been working on the theme framework to understand it and adopt it and make it into teaching materials. Okay. So the purpose of this course is we want to give you a tool so that you can design the neural network for a specific applications. Often when you design the hardware accelerator, the difficulty is how to use it from the application layer. For example, suppose for a neural network, you have an idea that a certain layer I want to do the hardware acceleration, and you design a layer in the neural network. But how to have the whole network or application can use your hardware accelerating layer? So that involves the compiler. Okay, so actually to design this hardware, it takes whole company to make the become application usable hardware acceleration. Yeah. So this give you a very handy tool. So for all your neural network application in the future. Yeah.
Excuse me, teacher. You
Yes.
don't change pages.
Oh.
You have to
I
touch.
forgot to start. Oh, I forgot to show the nice picture. Yeah. So this so you will see there will be a lecture in the at the end of November and December. So you can look forward to it. Yeah, it's a very useful and handy tool. Yeah. And the next is a RISC-V. Okay. Why I'm interested in a microprocessor? Let's see that right now we design today's all the hardware acceleration framework is built upon an current I/O architectures. Okay, for example, the PCI accelerated card is put on the PCIe bus. Okay, so there are a lot of effort or overhead in using these hardware accelerators because you need to move data to the processor, and the communication involve layers like operating system overhead. Okay, so you need to be very skillful in system architecture design in order to eliminate all those. I think every time I turn the page, I need to put a dot. Okay. So so it's really not an optimized architecture. So we need to have the computing, the accelerator close to the general purpose processor. Because you cannot run the system without general purpose processor. Okay. So next step you may make it as a co-processor. Okay. Co-processor, you just move it, you don't have the I/O bus, but it's still another bus. Okay, so the ideal acceleration will be inside the processor pipeline. Suppose you design an accelerator, and you make the accelerator as an instruction or macro instruction. Okay, and put that in the processor pipeline. So that's the most optimized architectures. Okay, so in that case, you need to have the capability to design your own processor. Okay, so that's why I'm very interested to have a high-level synthesis processor. Yeah. So this student also from next course, their final project, they put a brain prediction in the RISC-V processor, and this RISC-V processor is developed in high-level synthesis. Okay, it's a very good, yeah. And actually, this processor is from an instruction set simulator. You know, when you design a processor, first you design the instruction set simulator to make sure you have all the instruction set developed correctly. Okay. So, and then people take your instruction set manual or document to design the processor to make sure the instruction is compatible. Okay. So why not we just simply take the C code, C++ code of the instruction set simulator and turn into the actual design. So in that case, the processor will be developed completely compatible with the original instruction set definition. Yeah. So this is an effort. People take a RISC-V, simple RISC-V instruction set simulator and turn into a hardware using the high-level synthesis. Yeah. So this is also very interesting project. So if you have a RISC-V and it's written in C++, then you can do a lot of interesting work with this RISC-V processor at hand. Yeah. Okay, so this the next one I'm talking about the quantum computing. This is a simulated quantum. Yeah, it's using the AAHLS. AAHLS is a general methodology to do the combinatorial optimization. So any problem can be formulated as a QUBO problem. Okay, most of the application optimization can be formulated by the QUBO. Then you can use an EC model to solve this problem. Okay. Then so this is I asked this student to also make this as a teaching material, and they will guide you step by step how to do the optimization, including the scheduling data movement. Yeah. So one promising application is Toshiba using this for the finance, mainly the currency arbitrage. So currency arbitrage actually is a graph problem. Yeah, you want to find a path that give you a positive gain. Yeah. So so second part of the course, you will be learning these three topics. Okay, let me talk about the lab. Okay. First, the tool. Okay, I suppose before start the course, every one of you should install this tool. Okay, this is a very handy tool that you can install in your notebook, so you can do the experiment everywhere. Okay. And even though you want to run in the actual FPGA device, we right now put the FPGA in the lab, so you can access remotely. So you don't need to carry a FPGA board with you. Okay. So it's a very convenient. Yeah. Okay, I talk about the lab. We'll be using two platforms. One is the Pink Z2, is a MPSoC. MPSoC means that they have a SoC inside the FPGA chip, so they have a processor. Yeah. So that's an embedded system. Another platform we'll be using is used in the cloud. It's a U50. It's a PCIe accelerator card. Okay, so we will be using these two platforms. So with these two platforms, basically you address all the application acceleration platforms. People just use these two platforms. Okay. So the lab also put into three groups. The first group is just get you familiar with the platform and set up the tool. The first lab one, just install the tool and run very, very simple example. Just run a multiplier. Yeah. So the purpose is simply to test the flow. Okay. 诶，怎么回事？What happened? All right. The sharing. All right. I still can share. Oh, okay. Yeah. So that's the lab one. And lab two, you develop the very simple HLS code, basically running a FIR filter design and run on the Pink Z2. Yeah. So in this lab, you want to you will get familiar with the XI master and string interface. Yeah. And also you need to this lab also teach you the whole embedded system, the software flow. Okay. Basically, you need to understand how the kernel communicate with the application program through the intermediate software driver and the hardware supported. Lab 3 is a cloud application using the U50 PCIe card. Yeah. So the host program is running OpenShield. Yeah. Okay. Yeah. And this lab give you the code. The kernel code is a very good template. Then you can use the lab 3 code for your application accelerator. So the structure, you just use it and change certain parts for your different application. Okay, the second part of the lab A, B, C, the purpose is you will have you need to learn advanced tool usage and all different techniques to do the kernel optimization. And more importantly, you will be learning the software and hardware system co-design issues. Yeah. And in the first part, lab 1, 2, 3 is an individual lab. Okay. Okay. The lab A is using the UGA71, and they are the following topics. Okay, you choose one topic to work on it. And for other topics, you will be learning from the class because you guys gonna to give a presentation to teach other students about your experience using this running this lab. So this give you a very that's a very introductory lab. Okay, not very complicated, and the document describe very detailed. Okay, so it won't take much effort. Yeah. And the second lab is more complicated because the lab B adopt from the VT's tutorials, and those lab has been years, so it's well accepted by the industry. And I look at the content, I think it's very good, and the document is also well written. And yeah, it teach many important concepts for the system design and also the kernel optimization. For the kernel optimization, they use this example. This Cholesky algorithm is doing the matrix decomposition. Bloom filter is used for data analytics. Convolutional filtering used a lot in the neural network and video image processing. And traveling salesman problem is a graph problem. Okay, so people use this graph algorithm to do a lot of data mining. So those algorithms is a little bit more complicated, and yet is very useful. And you use a lot of high-level census design techniques inside. And other than that, you have a lab doing the system hardware and software co-design issues. So you can think this is an advance of lab A. Yeah. Again, for this lab, you choose one topic and work on it. And I want all the students cover all the topics. Okay, not all the students choose one topic. So I want to average out. Okay, so maybe you may not be able to choose the topics you like to do because people already choose that. You don't have the slot to choose it. But don't worry that you can learn all of the topics from other students' presentations. Yeah. Lab C is a very it's a much more complicated. It's we will try out the VT's library. Okay, VT's library cover in those areas. If you look at closely, okay, there has some common library like a math library, okay, linear algebra, statistics, DSP, and data management. And built on top of it, you have a domain-specific library like for the vision image application, quantitative finance, data analytics database, data compression, data security. Yeah. And each of the library, they cover 3 levels. The level 1 is the module level, a very simple specific computation. And then you have a level 2 is the kernel. So a kernel will use multiple modules. Okay, and then level 3, we are talking about the API and application. So doing this lab, basically you exercise what I mean end-to-end application. You go through all the flow from the hardware module to how the application can use it. Yeah. So with the background you have been doing level A and B, I believe you will well capable of doing level C, but it's quite intensive and extensive. Okay. So after the lab C, I believe you are all capable of design the end-to-end application program. Yeah. Okay, and the lab group 3, so basically that's the application cases. Yeah. So lab D, I really want to have the Fin framework, give it to you, so that you can use this platform. I believe it's gonna benefit your future research or development. Yeah, this is a very good tool. And we all know Xilinx VT's AI, they do offer the whole infrastructure to support to run the AI applications. Okay. However, the VT's AI tool, the DPU is not open source. So that means you could not design your own neural network. Okay. And in that case, that also the DPU is a AB neural network. So it's still it's kind of for data center use. So we are talking about AIoT. We want the AI engine is small and can fit in the very small and low cost FPGA. And they can offer all kinds of application at the edge side. Yeah. Then, so the Fin is based on the BNN, is a binary, single bit neural network. And there are certain applications run well with with the BNN, not all the application. Yeah. But for those users for edge end, many applications can use the BNN. Yeah. So that's so in case you guys want to go out start a company to develop a spatial edge device with intelligence. So using Fin is pretty good. Yeah. So you use a very low cost FPGA device. Okay. All of the lab I just talked about. There's all requirement. The next one, the RISC-V is optional. You don't have to do it. The purpose, I want you to use it, to put this framework at your hand. So in the future, you can use it. And the SQA is the option lab. Okay, and then we're talking about the final project. The final project got to be end-to-end application solution. So you basically identify an application is interested, you are interested in, for example, blockchain, okay, or any application or something related to your research. Okay, so you are given a source code from an application, then you take steps to profiling and identify the function to accelerator. And then you see how to partition and co-work with the application program. And next step, to do the kernel optimization. So the whole thing, the whole application runs transparently, like without the hardware solution. So you have to figure out how to integrate the kernel application, a kernel function into the whole application process. Okay. So I advise that you put your research, you identify use this for your research project so that you don't duplicate the effort. So you spend actually doing the final project does take a lot of effort. You want the effort can be toward to your research project, your master thesis, so anything that you like to do research on. Oh, I didn't change the screen when I talk about the final project. Okay. Oh, and here I'm talking about the engineering soft skill, and I highly value those skills in my engineering career. First is problem solving. Okay, the problem solving start with how to ask the right question. So in this class, you're gonna to exercise this. Yeah. And then another is presentation and communication. Okay, just a few days ago, international, the world largest headhunter company come to me. They want me to teach the presentation and communication. Yeah, I told them that I'm an engineer. I quite technical. I'm good at the technical, but I never do the presentation and communication. And the reason why he came to me is a company want them to find the lecturer, the teacher, especially with strong technical background. They want to teach engineer how to do the presentation and communication. Okay, so it's a critical for every engineer to be able to present idea clearly and convincingly. And to tell the truth, when a company want to sell a product, a good communicative engineer come with the sales is the most likely they were successful to get the customers. Yeah. So with this skill, they also expand your future career probability. Okay. So this definitely you will exercise that because every one of you will be giving presentations. Critical thinking will be demonstrated in the lab in your presentation too. Because when you solve a problem, you got to explain clearly what is your observation, what is the reasoning about it, and why you decide to solve this problem with this approach. Okay, so the thinking process in this class, you're going to demonstrate you do have a critical thinking capability. Okay, the professionalism, courtesy, and collaborative teamwork. Actually, I teach this course last year, and I observed that all the students are working very hard. Okay, but one thing I've observed is that they don't ask for help, and people don't offer help voluntarily. Okay, it's quite different from because I work in U.S. company before. Okay, let me tell you one example. When I start working in USI Logic, there is an engineer who graduated from college only, graduated from Tech. It's a very good college. And I observed that whenever an engineer quit, that engineer take over his job. So no problem. Okay, his work I can take. Okay, and also he often roll a tool. The tool quite handy because when you're doing the software development, you want some handy tool to do some kind of automation. They often, a few weeks, they will write out an email say, hey, I wrote this tool. This tool is quite helpful. Help me a lot. I'd like to offer out so you guys can use it. Yeah. So this kind of engineer, and then later he came to Synopsys. He's one of the Synopsys founding engineer. Yeah. So he's very capable and very willing to help. That's the role model of an engineer. In my life, yeah, I admire this kind of engineer. So I want every one of you can be an engineer like that. In that case, you definitely will have a very promising future. Yeah. So so I want you to exercise these two attributes, two characteristics in this class, and creativity. Yeah. So these are 6. always keep in mind. That's I highly regard the person with this mentality or skills. So to put this engineering soft skill in practice, I do offer grade points for those. So the problem, how do I grade it? To give you points for that. I haven't finished thinking all the items. I just come out the following. First, I like you to raise sensible questions, either in class. In class is my most favorite one. Okay, so when I was young, as a young engineer, I went to attending the international conference. I remember one time I went to an Intel conference, and in the conference there are several hundreds of audience. Okay, I encourage myself, why not I stand up and ask questions? So I stood up and went to the microphone and asked the questions. I don't know whether other people understand, but you know, the presenter is quite courtesy. They probably they don't understand my question, but he still give me an answer. Yeah. So try to. I know most of you don't like to speak in public. Okay. Why not take the chance in this class? Stand out and ask question. Yeah. So ask the question. You can ask the question in class or in the cool class discussion forum, or even you can send out the question in the Xilinx developer forum. Because the HLS, to tell the truth, in the class, most likely the issue you run into, no other student, even me, I could not answer your questions because it's evolving and there are many things that we haven't tried out yet. Yeah. The only place you can seek your solution is right to the forum. And Xilinx engineer will answer that, or other experienced people can answer your question. Okay, another way to earn the points is offer help to solve a question. Okay, and the next is give the feedback on when you read the textbook. Send me your feedback. I will send out a form so you fill out that what problem or mistake or area for improvement. You can write the feedback. You can even share new findings or other resource, just like I said, the SI logic engineer, he wrote a small handy tool and then offer to other. Or you find out something that's very helpful for learning HLS, you can post it. Yeah, all those behavior is greatly encouraged, and you can earn points for that. Yeah. Okay, grading. So the grading total, I'm quite generous. It's over 100. It's actually 115. Yeah. And for those lab, okay, that's how you accumulate your final grade points. And most of it from the lab, okay. And we have a final project, okay. Final project is biggest portions, and we have a midterms, and we have a soft skill 5 points. For those marked in yellow, is actual credit. So that's how the total credit up to 115. So the yellow part is 15. That means those parts you may not need to do. Okay, even though you don't do any of the yellow parts, you still can get 100 points. Yeah, but you can use those actual efforts to compensate the area you did not do well. For example, you miss your midterm, yeah, then you ask few questions to cover up your midterm. Yeah. So you can, so after this table, I believe many of you have an idea or strategy how to get those points. Yeah. Okay, at the end, I'd like to introduce Xilinx Adaptive Computing Challenge. The Xilinx PM sent me this invitation. He asked me to invite my student to attend the competition. The offer is quite generous. Yeah, the first prize is 10,000 US dollars. Okay, and look at the schedule. Look at the schedule. I believe still it's likely, very likely you can attend this competition. You just turn on the application by you have 2-3 weeks to turn on the application. So right now, think about, and you can go on the website, this website, and look at what other people can submit for the competition. For the competition in the past years, so you get an idea what other people is doing, and then think about what you will be doing in your master thesis or any your research. Okay, if you find the synergy of it, then it's likely you can participate in these applications. You simply use your research for this competition. This is not the actual efforts. Okay. So just in the application is not complicated. It's not no detail on how you implement that. Okay, look at the submission date. It's February 28th. So it's the semester finished and your final project has already turned in. So you have plenty of time to prepare for this competition. Yeah. So use what you learn from this course and give it a try for this competition. Yeah. So if you decide to go abroad to study in US, this record is a very good record, and often those big companies will come to you because today is the big US IT company. They find their talent not by the resume they review. They actually actively go out and seek talent from the open source, from those competition winners. Yeah. Okay, so this ends my the course outline. Is there any questions?
蔡依林
Oh,
raising.
Yes.
yes. Hey, Jiafu, you need to make a record. Everyone raise a question, write down. We start accumulate students' points.
Okay.
Oh, so am I allowed to speak now?
Yes.
Oh, okay. I'm just wondering that because we have the credits about the soft skills part, so I wonder how this part will be graded. Thank you.
Okay. Let's go back to this slide. Yeah. Okay. So here, that's the list things that I can for those for those soft skill, some of them covered by your presentation, so it doesn't count. It already reflect in your grade for that presentation. Okay. So we count the point for those items, but I may add some other instance that you can earn points. I just give a very brief thought on those areas. So for example, you raise a question, then we have a record that you ask a question in the class, or yeah, or a question in the class discussion forum or you offer help or solve questions. So we will have a record that how many points you accumulate. Yeah. So at the end, then we will do the property normalization among all the students, and then assign the final grade point from 1 to 5 here. Yeah, the soft skill, the total is final is 5 points. Yes, that's what I'm thinking about. And do I answer your question?
Okay, yes, thank you, Professor Lai.
Sure, yeah, thank you. Okay, so if no more question about the course plan, then we go to next topics. Okay,